Okay, let's get on with the lecture today, physics. What's that got to do with? What's got to do with this quantum dot? What the hell is a quantum dot? Is that something like the geometric point? Is that what that's all about? I mean, here's the geometric point. Is that what the quantum dot is? After all, whenever someone says in geometry, mathematics, whatever, right? They say, what is a point? And they take the pen, and they hit the paper or they hit the chalk on the board or maybe a crayon against a piece of carton there, and they'll say that's a dot. Well, there you see a dot. Is that the point? And the point is a dot? Well, there is a difference, you see, because the point, geometric point, as we've covered it recently, right, is zero dimensional. It's zero size, no radius, no nothing. That's what the point is. What is point? It's a location. Is that what a dot is? A quantum dot, right? Is that what a quantum dot is? Just a location? I mean, they're talking about quantum, right? And we've covered it this week. The quantum dot, apparently, according to the definitions that are out there, are greater than zero size. But the quantum particles, like the point particles, electron, gluon, quark, those are all zero dimensional, zero, nothing. In fact, they're not even particles. What they are is wave function collapses, whatever that means to you. You have an equation that collapses, a probability, or I don't know, you can't even picture it, and you can't. It's nothing. It's a zero dimensional, no size, nothing. And they do use the word infinitesimal in these situations. They like to use the word infinitesimal because it gives you the idea that, well, no, it's not truly point particle. It's not zero dimensional. It's just infinitesimally small. What does that mean? Well, that means it's approaching zero in size. Approaching is not zero. In other words, approaching zero is not zero, exactly zero. There's a difference. Approaching zero means it still has size. But they use the word infinitesimal, which is very extremely misleading. And why did they do that? Well, they want to give you the idea that it's an observer related issue, that you can't really see it very well. No kidding. You can't see an atom very well except like from a telescopic view, like an eagle would see it, from far away. We can see atoms like that. We have imaged atoms like that with atomic force microscopes and so on. But to see an atom up front, like one atom with all the little electrons rolling around, never seen that, never filmed that, never been able to image that. And because we can't get close enough, we don't have the resolution to see that. Okay. So the question is, the quantum dot the same thing as the geometric point? And the answer is no, because the geometric point, as well as the quantum point particles, they're all zero dimensional. They're, you could say, non-dimensional because they're really talking about concepts. Wave function collapse, what the hell is that? That's not a physical object. On the other hand, the quantum dot is used in technology. And they don't claim for it to be zero size. So one of the issues you got to think about today, why do they put the adjective quantum? Why do they call it quantum dot? If it's, it could be a dot, but certainly not quantum. Quantum has to do with, I mean, this could be a classical dot, but not a quantum dot. Quantum mechanics is understandable. You can't understand, you cannot explain quantum mechanics. And here, the dot, as you're going to see, we're going to be able to explain the classical part, but what we're not going to be able to explain is the quantum part. Okay, so let's move on here. So what is a quantum dot? Here it is. Okay, here's your quantum dot. It looks something like that. Quantum dots, nanocrystals, 2 to 10 nanometers in diameter. Nanometer is, you get a centimeter, millimeters, you get smaller and smaller to micrometers, and finally at the 9th decimal point, you get the nanometer. So it's a very small thing, anywhere from 2 to 10 nanometers in diameter. Okay, so what are we talking about? This is not zero size, obviously. Okay, and so they're saying we got something there. Okay, at least it's defined that way. And they're nanocrystals. So we're talking about crystals, meaning that the crystal is made of many, many atoms, not to mention molecules. So you're talking about something very small, but it is made of atoms. Okay, when exposed to light, quantum dots emit light of particular frequencies. Okay, so you have the wavelength, and different wavelengths have different colors, and you can also say that different frequencies have different colors because according to the equation, velocity of light c, right, equals to what? Frequency times wavelength. One goes up, the other one has to go down. They're inversely proportional. So when you increase the frequency, the wavelength goes down and vice versa. And, you know, high frequencies, long wavelengths are, you know, identified with low end of the spectrum, reddish, I mean for the visible light. And the, did I say that right? High frequency is the blue, whereas low frequency is the reddish end, and vice versa for the wavelength. Wavelength, if it's long, it's reddish, and if it's short, it's bluish, okay? So that's essentially what the spectrum looks like. And what these people say is that when exposed to light, these quantum dots emit light of a particular frequency. Okay, so we have the electromagnetic wavelength, you know, which is color, a measure of color, right? Mathematical measure of color is emitted, and it's dependent on the particle size, they're going to say. So it depends on how big this quantum dot is. The higher it is, it's got a different color than if it's low size. Okay, so big size, low size, it changes the wavelength. Okay, and it's also precise control of size and what? Shape. So they're talking about size and shape. Okay, and the way they do that is adjusting reaction time and conditions. But we're not interested in the technology. We don't do technology here. We're not interested in that at all. We want to know what is the mechanism that they're going to use to explain what's going on in that micro world, subatomic world, or even an atomic world if there is, like, you know, interaction between atoms. We're interested in that as well, right? Okay, so first of all, here again, a little more technology, how they build these things or how they make them. Quantum dots are nanocrystals. Again, they're crystals, meaning they're made out of many molecules or many atoms, okay? Made by combining metals such as lead or cadmium with other elements including sulfur, selenium, and arsenic. And there on the bottom you have cadmium selenide, okay? That's one of the compounds with which they make these dots. Okay, by controlling the ratio of these starting materials, the temperature, and the reaction time, scientists can generate a nearly unlimited number of dots with differences in an electronic property known as band gap. And we'll explain that in a second, which determines the wavelengths of light that each dot will absorb. And my first issue is, why do they call them scientists? What's this got to do with science? I mean, these people are technologists. If that's what they're doing, they're developing, you know, crystals. What's scientific about that? That's like going to the patent office and saying, look, I built this little crystal, and I did it by putting all these molecules together and building up this little ball of crystal ball, right? That's technology. What's that got to do with science, with explaining the mechanism of how one of these things works? Why does wavelength have to do with the size and shape of these nanoparticles? That's what we would like to know. That's what we would like to understand. That's what we would like for someone to explain, and they don't do that. Okay, so this is where we have a little bit of problem with these folks. Okay, here's an illustration of what they just said. You have light coming in, and they built these little balls that have all these little layers, okay, of molecules. These are the so-called crystals, okay. And this is in general terms how it's going to work. Okay, they're just going to build these things. And again, we don't care about the technology. We don't care how they're built. We don't care what chemical element they use specifically. Not so important. We want to know the mechanism. Okay. So what is it? What is the mechanism that these people are going to talk about? Are going to explain? Well, here's one. Okay. So the quantum physical interpretation. Okay. Under the influence of light, electrons are excited. Okay. Whoa, they're excited, and quantum jump up to a higher energy band. Whatever that is, okay, we'll find out in a second. Electrons can also fall back to a lower energy state or recombine and re-radiate. Okay, so this is how they're going to play around with that. Okay, so what do they mean an electron is going to go up and an electron is going to go down? What the hell are these people talking about? Okay, here we have an idea, okay, a little more detail. A band gap, what is that? Well, you have two things. You have the conduction, let's start at the other. You have the valence band, which is the outer layer of an atom. It used to be, at least, in my days, but from there the electron can move to the conduction band. And the question is whether the conduction band is part of the atom or part of the flow of current. I mean, does the electron stay in the conduction band and keeps whizzing around the atom, or does it fly away? Okay, so this is important because they talk about the electron jumping up because, you know, you hit it with energy, you hit it with this photon, this ball of light, It imparts energy to the electron. The electron now moves from the valence band, outer orbital of an atom. This is the outermost orbital, and it's going to move it into the conduction band, whatever that is. What is the conduction band? Does that mean that now we have a higher level of energy there, that the electron continues rolling around the atom in the conduction band? Or does it fly away and become part of another atom? Does it flow? Electrical flow is what? The flow of electron beads, right? So what happens to that electron? Okay, does it stay there? Well, this is the band gap, which is the difference in energy levels, mathematics, nothing to do with physics. This is just an accounting procedure here, between the top of the valence band and the bottom of the conduction band, determines the wavelength of the emitted light. Okay, so you can see that there's a difference, the energy, that so-called energy, which is what? It's light coming in. It's a photon. Why they draw it as a wave, I have no idea, because I thought the photon, when it hits the surface, in this case, it hits an electron, very good accuracy. It just hits it right. I mean, electron beam, we can't even measure. It pinpoints nothing, right? And here we have a photon, which is another nothing, and this nothing hits this other nothing, bumps it off into the conduction band, or a higher energy level. Okay, that's the explanation. This is their physical interpretation. And here's a little GIF on this, showing you, the differences. In an insulator, the band gap is too big, too large, and so it's very hard to knock an electron from the outer valence level to the conduction band. Semiconductor, a little easier. How about conductor? Well, conductor, essentially the valence band and the conduction band are one and the same. Okay, so they're like iron. Iron has conductor and valence bands are the same. And here you can see it. Yeah, you see how with a little bit of energy you knock electrons from the valence band into the conduction band, and now they're going to start flowing. Okay, you'll see this in a second. Here it is, and you can see the electrons are flowing. So they don't stay in a conduction band around an atom. They start flowing. And that's what we call electricity. The flow of electron beads. And you say, well, what's wrong with all this, Bill? It looks like a sound theory. One would think it's okay. You say, look, you got a little bead. It's going around the outer shell, obviously, because we're only talking about the valence band, the outer shell of an atom. Okay, irrespective of what atom it is, it's the outer shell. You hit it with a little bit of energy, meaning a photon, meaning a wave, whatever that is. You knock it into the conduction band. Okay, so now this little bead is in the conduction band. Now it's going to flow along the conduction band, and that conduction band is what we call electricity. Nothing wrong with that. But what happens? Because the difference between the conduction band and the valence band, it depends on what that distance is. Well, you have different colors of light, because the color of light is dependent, the wavelength, frequency, if you will, is dependent on that distance. Okay? And for conductors, obviously, that's much easier, because there's conductor and valence band are one and the same, essentially. Okay, where do we get all this nonsense from? Well, we got it from this. These are the notions that we have of the atom. It's the planetary atom that you see, and these are two different atoms that I found on the internet, and they essentially put the same thing. Everybody's using the planetary model to explain this. And so what is the planetary model? Well, as you can see there, it's got these circles, and those are the energy bands. Okay, those are the orbitals, meaning that it is an orbital in orbit. Not quite. It's like an orbit, but it's a region within which you can find the electron orbiting. Okay, that's the best way to explain it. And that's what you're seeing. You're seeing a cross section, in other words, a two-dimensional vision of what an orbital is. You're supposed to see this or imagine it, visualize it as a shell. Okay, but the shell, what is the shell? The shell is the orbital. And the orbital, you think of an orbit because you see the beads going around. Actually, no, because the bead is one thing and the orbital is another. The orbital is where the electron is trapped within. Okay, so the electron is trapped within the orbital. It cannot leave the prism. Okay, and it can move around in a region within the orbital, but it cannot fall to the lower orbital. Every electron is out there in his own orbital. Okay. And again, we have zero-dimensional electrons in their own orbitals. Okay, so these are the physical interpretation. And where do we get this nonsense? Well, we get it from these two gentlemen. and one is Bohr and the other one is Rutherford. This is where the planetary model came. Bohr, in what was it, 1911, he came up with the orbitals, the notion that an electron can fall from one energy level to another and back up, and when it does, it emits a given frequency of light or a given wavelength of light. So that's where this quantum dot got the idea, that electron is a bead that just falls from one energy level to the next, up and down, and when it does, it emits light. And the frequency or wavelength of that light is dependent on that gap, on that distance between energy levels. What did Rutherford come up with in 1919? Actually, he finally inferred it a few years later, but he said, look, this is the nucleus. And the nucleus is the center of the atom, and at the time he was thinking of maybe just a single proton in there, but here you have protons and neutrons, which came a little later. Chadwick came up with that idea, James Chadwick, of the neutron. And so one came up with a nucleus and the other guy came up with the orbitals, and they put them together, and that's the planetary model that we have today that everybody uses to explain, among other things, the quantum dot. Okay? Because what is it that we have to explain about the quantum dot? Well, we have to explain the wavelength, why this quantum dot emits different colors. Okay, why when you build it, when you make this technology, whether it's for screens or whatever you're going to use it for, why it is able to emit. And remember, it's not reflecting, it's really emitting different wavelengths, meaning different colors. Okay, that's what it does. That's the value of it. Technology, hey, love it. Science, where is it? We don't have any science yet. Okay, we don't have any explanation. And you say, well, why don't we have an explanation? Well, here's the problem. Here's the main problem that these people have to explain in a nutshell. The first one is, why doesn't the electron fall to a lower energy level automatically? Why doesn't it continue falling all the way down, in fact, to the proton? Isn't the electron negative, whatever that is? Isn't the proton positive, whatever that is, in physical terms? If we have negative and positive, I thought that negative attracted positive, positive attracts negative. Why doesn't the electron fall to the center of the nucleus where you have all these positive charges known as protons? I mean, it's a very simple question. Why doesn't it fall in there? And they never answered that question, which was one of the reasons they came up with a planetary model. And what did Bohr answer? Well, he said, it is so. He took his magic wand, which I don't have here for a second. I have it here. Took his magic wand and he says, it is so. And he was able to explain the spectrum of hydrogen because of this. But yeah, I mean, mathematically. But you still have not explained the physical process, the mechanism. And so, I mean, why doesn't the electron fall to the proton? Then you have the other issue. Why doesn't the electron go outside of the orbital? Why doesn't it fly away? So you have these two situations. Why does the electron stay within a given band? Energy band, energy gap, whatever you want to call it, I don't care, orbital. Why does it stay in that lane? Why doesn't it go outside the lane, and get an ice cream cone before it continues running? Okay? So it doesn't fall out of the energy band, orbital, whatever you want to call it. It doesn't fall inwards to the proton or nucleus. Why? What's preventing those two situations from happening? That's what we don't have an answer to today. And they never will. They'll never will. Why? Because you cannot explain it with particles, with discrete particles. That's where the problem is. Now, here we can explain it maybe by showing a construction, okay, of our version of that atom. And maybe I should put them side by side. Here's our atom. Here's, let's see, where was this? Yeah, here's the other one. Let me put this one over here. And this one over here. So this is their model, okay, the planetary model. And you can see our model, the one we're proposing in exchange, and why we are able to explain these things, such as quantum jump, and why we have certain frequency and wavelength. Because, every atom in the universe is bound by what we call the electromagnetic rope. Binds any two atoms. There you see the construction of the atom on the bottom right, okay? And one thread of the rope forms the electron shell, which is encapsulating the proton star, which is made by arbitrarily the electric thread, okay? And so the rope becomes an atom, and the atom becomes a rope, and so on down the line, forever. Now we can explain why when the atom expands and contracts, it emits light, frequency, wavelength. Why? Because it's the link of a rope. See, they cannot explain that. They cannot explain why the atom doesn't fall to the center of the atom. We can, because see, the balloon just expands and contracts. there is no, the balloon does not collapse completely to the center of the atom because it's got all these, I call them, I mean, you can think of it as a rolled up urchin, sea urchin, or maybe a porcupine. You know, all the quills are pointing outwards. And so the shell can only go so far back and forth, and what it does is just pumps back and forth. Okay? So it cannot collapse the electron shell all the way to the center of the atom. And when these people are talking about an electron bead, what they're looking at is one of the points, a location on the electron shell. That's what an electron has been all these this 100 years, these past 100 years. Okay, so you can see there's a difference, but see, we can explain action at a distance with this, which is one thing that the quantum model will never be able to explain. How does this particle over here influence that particle over there? How do you do that? This is the issue. And he cannot explain that. That's why they cannot explain gravity. Gravity, they know, they realize intuitively it's a pull force of some kind. How do you pull with particles? Okay, you got two particles, okay, here, okay. How does a particle pull on that one? Now, if they're connected, you know, by something you can't see or touch, now we can see why, you know, I mean, at least you can now imagine pull, okay, because that there is a mediator. The only issue is that we cannot see or touch that mediator. And so there is no real action at a distance, just we can't see or touch it, okay? Okay, what can we conclude from this? Well, here's the conclusions that I reached. The quantum dot is infinitesimally small, okay? Why do they use infinitesimally? Why do they talk about 2 nanometers to 2 to 10 nanometers? Well, they want to give you the idea that you can't really see them. They're little crystals, so tiny, you can't see them, so they're infinitesimally small, and they don't worry about the problem anymore because mathematicians, so-called scientists, they don't care about architecture, shape. They don't care about size, okay, meaning something greater than 0, and in that sense, size. And so they use the word infinitesimal to refer to these things. Why? Because the observer cannot see it. Now, they do need shape and size because on the one hand, it's immaterial to them, but on the other hand, shape and size are what make the quantum dot useful in technology. Remember, shape and size of the quantum dot, that's going to determine what color wavelength it emits. Okay, so we're not interested in technology, we're not interested in that part, we're interested in why does it? And these people are saying, well, it's related to shape and size. Okay, how is it related to shape and size? Why? What causes shape and size to change the wavelength or the frequency? That's what they have not answered. That's why they're not scientists. They're just technologists, people who are developing stuff without seeing. You know, they're blind. Okay. Quantum explanation, what is it? Electron jumps from valence to conduction band and back. Yeah, but see, in order to do that, they need the irrational planetary atom. Okay, and so they say different sizes and shapes of dots mean different wavelengths. Yeah, and why? Why? If they're going to use a planetary atom, they can only describe it mathematically and say, well, this is what happens, this is what we measured. But they cannot explain the process with discrete particles. Okay, so no, quantum dots are technology, not science. And the fact that they use quantum, the adjective quantum, that they put that in front of it, is very misleading because people approach you and you'll say, well, hold it, quantum is irrational, blah, blah, blah. And they'll say, well, no, but we have quantum computers and quantum dots. And they use that word quantum, they think they're talking about science. You say, well, okay, so we have quantum computers and quantum dots. Yeah, you wouldn't have a computer if it weren't for quantum. But see, they don't realize that computers are classical objects that we can see and touch and manipulate, etc. It's what we're trying to figure out is what happens at the genuine quantum level. In other words, what happens at the atomic and subatomic level? That's where we're stuck. That's where we can't get an answer from them. So if the computer works, it works because of transistors, not because of quantum. Quantum is something else. Quantum has all these weird explanations, physical interpretations for what happens at the subatomic level, at the level of light or gravity, which they cannot explain. Okay, that's where quantum really, that's its realm. Not here, not at the classical level. And this so-called quantum dot is a classical dot because it's a crystal that has size and shape. None of the particles of quantum mechanics has size or shape. If you don't believe me, just go to a standard model and tell me what an electron looks like. Do you see a shape there in the standard model? Do they have a nice little picture? Especially when the Swedes, I think university, or they wrote a paper showing that they were able to film an electron. Good. You filmed an electron, you should be able to tell me what an atom looks like and what holds the electron to the atom. And you cannot say that the electron is zero-dimensional point particle if you filmed it. Okay? So this is where the problem is. Quantum dot does not belong to science. It belongs strictly to technology, and it should be called a classical dot.